This is Chapter 13, Climate, Weather, and Their Influences on Geology. Our goals for this chapter include to introduce the linked system of atmospheric winds and ocean currents and look at their control on weather. We will also investigate the causes of hurricanes, tornadoes, and storms, and deserts and rainforests, and we'll look at their locations on Earth. And we'll work to understand the evidence for climate change over time. So we'll look at this area. This is India at the center. And we'll consider what different climates are likely to be present and what controls them. This region actually has the most extreme topographic changes on Earth, and it has large rivers that carry sediments from the high mountains in the Himalayas to the Indian Ocean. And of course, India is surrounded by ocean on two sides, so it has the oceans actually have a huge influence on its climate. We can find dust storms with the prevailing wind direction, where sediment's carried with heavy winds. That would actually blow off India's northwest desert. And remember that the Himalayas were formed because of the collision between India and Asia, a continental convergent boundary. Off the coast of Africa into the Indian Ocean, we have nutrient-rich seawater, which causes algal blooms. And we also have rainforests covering many parts of the subcontinent. Additionally, flooding rivers are pretty common on this river in particular, which is a massive river system that transports a large amount of sediment from higher elevation to lower elevation. And of course, there are high mountains, which controls where wind can go, where air can stop, really. All right, let's talk about air pressure. Pressure itself is a force exerted on an area from all directions. With gas, it's related to the collision of molecules. So we have this diagram here, a cylinder with the ability to compress it like a French press for coffee. If you compress a gas into a smaller volume, you have more collisions of molecules per area, and that would be your pressure increase. So if you look at these cylinders, if gas is heated, molecules actually become more energetic. They will have more collisions, and that results in a higher pressure within the cylinder. If the gas cools down, the molecules become less energetic, so you have fewer collisions and lower pressure. So we're heating to the right and cooling to the left. And we're going to look here at different layers of the Earth's atmosphere and what's associated with each. So you have temperature on this sort of left axis, and then altitude as well on this axis. And we'll note that the number of air molecules decreases with height into the atmosphere. Okay, so the atmosphere contains clouds, weather, the Earth's surface, and us too. In the troposphere, getting into the stratosphere, that contains the ozone layer. It becomes warmer as you go upward. And then in the mesosphere, that's the site of most shooting stars. It gets pretty cold up here. Into the thermosphere, where you'll actually get the northern lights originating at a very high altitude. This classification system focuses on the way in which temperatures and the abundance of matter vary with distance away from the surface of the Earth. Keep in mind that atmospheric pressure decreases as we go upward and we have less molecules up there. All right, so here's a map of air pressures on a given day. We'll note the features, the main patterns, and the values of the lines. These lines are representing lines of equal pressure, just like your contour lines in an elevation map. A line of equal pressure is an isobar, and you can have those be valued in millibars as a unit. So the center of a high pressure area, we have H there, can define an anticyclone or a ridge. And then a center of low pressure, denoted with an L, would be a cyclone or a trough. So ridges and troughs. The average pressure that we have at sea level is 1,013 millibars, just for reference. Okay, air pressure and horizontal motion. So air pressure is going to vary, in this case, laterally between adjacent areas. It changes. So molecules that are in gas, such as in the atmosphere, will always attempt to go from higher to lower pressure. So gas molecules in an area of high pressure tend to spread out, again, flowing from high pressure to lower pressure. And that causes wind with these movement of molecules. The most efficient path for this transfer to take place is perpendicular to the isobars. If you only have a pressure difference and nothing else really going on, wind would blow perpendicular to the isobars. If your isobars are very close together, you can have a steep pressure gradient represented that way. If the isobars, the change in pressure, it's very far apart, it would be a gentler, more gradual change in pressure within a given area, just like with contour lines on an elevation map. Okay, so let's think about local winds along coasts. During the day, land is heated by the sun. That causes air to rise, which causes lower pressure and wind from the sea to come inward. We have sort of a low moving into a high like that in a unit there. All right. And the land is going to cool down more at night. So the air sinks, pressure increases, and blows out to sea. And that is a land breeze by contrast to this sea breeze represented up top. This is showing us global wind patterns. So the yellow arrows on the left indicate the direction from the sun reaching the earth, sunlight. Keep in mind, hot air rises and cool air descends. With that, you get these unit cells, these flow cells of air across the globe. And warm air in general, heated at the equator, rises and flows north and south. As it rises, it cools, descends, and flows back toward the equator, forming a belt of easterly winds around the equator. And then the flow from the equator is not straight north or straight south, but it ends up being deflected as the Earth rotates. So flow is deflected by Earth's rotation. The equatorial regions get heated more than the poles, which gives us an overall flow of warm air away from the equator and then cold air moving away from the poles. We also have prevailing westerlies. That would just be winds from the west, and that's in the northern hemisphere, and then prevailing easterlies to the south, where you have dominant winds from the east. All right, the Coriolis effect. The atmosphere rotates around with the Earth, so it's always moving in an easterly direction because the Earth is rotating eastward. The magnitude of this motion is greatest at the equator because the air there has farther to travel around. And then the eastward velocity decreases gradually towards the poles. So the air flowing toward the poles is moving faster than the ground, and then it becomes deflected to the right. And this variable eastward flow toward the north or south pole results in polar flowing air that deflects to the east in the northern hemisphere and then to the west in the southern hemisphere. So the Earth is rotating, and that's really a good summary of how air is impacted by the Earth's rotation, and it results in what we call the Coriolis effect. Okay, so thinking about water, we have three phases of water here. Solid water being ice, liquid water, and then water vapor. So with evaporation, that occurs as water molecules escape as a gas, which is the vapor, from liquid water. And evaporation from the ocean surface is the primary contributor to water vapor in the atmosphere. Now, three phases of water can exist together at the Earth's present-day temperatures: ice, liquid, vapor, or gas. What we have here is just showing you a diagram that represents the state or phase of water under different temperature and pressure conditions. So, if you have a low temperature, you're going to see ice mostly. Unless your pressure is extremely low, you might get water with a low temperature as well. As you increase temperature and you increase pressure, you can see you go from liquid water to water vapor. And in this lower diagram, red arrows here indicate that the air heats up, passing from one state to another, and the blue arrows indicate that air is cooled, or rather that heat is extracted from air to allow the change of state or change of phase to occur. So we have some directional guidance here. And that also shows us how precipitation from vapor can heat the air, which is a necessary step in the formation of hurricanes. Also, evaporation of liquid requires energy, so that will actually cool the air. So melting of snow or evaporation of a liquid requires energy. We'll have the air temperature go down, and we call that evaporative cooling. Now, precipitation, we can say that involves three sizes of particles. You have a typical raindrop, which is 2 millimeters in diameter. You can have cloud droplets, which are on average 0.02 millimeters in diameter, and then condensation nuclei, which would be 0.002 millimeters. Okay, as a summary, the raindrops, of course, are large enough to fall. Cloud droplets are too small, they just stay aloft. And then the smallest are condensation nuclei, like dust particle in size. Condensation of water vapor can occur more easily around these solid aerosols, such as dust particles. These types of particles that encourage condensation then would be known as condensation nuclei, represented here. Raindrops can grow larger by incorporating other drops. We did speak to the water molecule's polarity and how it's able to sort of attract molecules into solution through dissolution, and then it also can grow with itself like that. Those drops can become smaller if they're split apart, of course, or they might not change in size, but throughout your life I'm sure you've noticed some rain events have very large raindrops and some much smaller. So how does water move between the surface of the earth and the atmosphere? Starting off, sunlight kind of drives the system that we're looking at. It liberates vapor from liquid water. And then prevailing winds carry the vapor-rich air onshore. The air is forced to climb over topographic highs where atmospheric pressure is reduced, which forces the air to cool. And then the vapor precipitates into liquid water and falls as rain. Whoops, I got ahead of myself. Okay, so the windward side of the mountain range receives most of this rain. And then on the opposite side, it actually gets a lot less rain because of what we call a rain shadow. You can see that here. So you might have desert-like conditions on the rain shadow side of a mountain. Okay, you might have heard of a cold front. If you watch the news and the weather, they talk about a cold front coming in. Fronts are boundaries between two types of air masses, such as warm, humid air mass and a cold, dry air mass. So with a cold front, cold air moves and displaces warmer, moist air. Cold air lifts warm air, forming clouds and precipitation. And then the location of a cold front on a surface is shown as a blue line, with triangles pointing in the direction of movement. Perhaps you've seen this on a weather map before. And then there's uplift of warmer air represented as well, occurring at a relatively steep angle. That can contribute to the formation of vertically oriented clouds that are above the frontal boundary. With a warm front, warm air moves and displaces colder air. So we got our orange arrow to represent that, and these little triangles showing the direction of movement as well. So warm air rides over cold air, forming layered clouds and precipitation. Like I said, the location of the warm front on a Earth surface map even is shown as a red line. In this case, I guess they weren't triangles. They're semicircles pointing in the direction of movement for clarity. So we have both represented on this diagram, and that gives you a stationary front. That's a boundary between warm and cold air, but nothing's moving there for hours or days. Personally, that's something I dread. I don't like it when the air doesn't move. I need a little bit of a breeze, preferably off a lake. So the warm air here overlies cold air, forming clouds and precipitation. And remember that this is going to be represented on a surface with a red and blue line, with the blue triangles and the red semicircles pointing in opposite directions, and that's a stationary front. This is a weather map, We can identify the fronts here and indicate which way the air is moving and what's occurring along each front. Well, in this case, we have a cold front moving to the southeast because we're looking at the direction that these triangles are pointing. And then warm air with a warm front is moving to the north. This is another way you can represent a stationary front, just kind of alternating the semicircle and the triangle. Cold air was moving towards the west here, and then warm air was moving to the east based on that. I know my stuff says things opposite of that, but you have to look at the direction that these shapes are pointing. So I'll fix that. Okay. So you can consider as well how large-scale atmosphere circulation might affect precipitation. This is where we really start to put the basics together to understand how this works. Okay. So in the area north of 60 degrees north, up here, cold air descends at the pole, and then surface winds bring this cold air south. We can kind of see that here. Between 30 degrees and 60 degrees, north moving air at the surface meets the air flowing south from the pole, which causes the air to rise and cool, thereby promoting rain and snow along that boundary. And then near 30 degrees north, we have two cells with descending airflow. This actually dries out the air and results in low rainfall. And then sunlight has its maximum heating effect at the Earth's equator, where rising heated air causes locally heavy rainfall. So yeah, that would be at the equator. We're going to find more precipitation to answer this question. And we're seeing around 60 degrees south and 60 degrees north, the same situation. Remember that you have dry situations where air descends, represented by these blue areas. We can't see the dry area near the South Pole due to the tilt of this diagram. Okay. You can therefore expect it to be drier at 30 degrees north and 30 degrees south. So what is a hurricane really? Hurricanes have a tremendous amount of energy, which they obtain from warm ocean water. You have an area here where warm water evaporates and water vapor rises from the ocean. As the pressure decreases, the vapor precipitates as rain, but the air heats up, causing it to rise again. And then the newly heated rising air draws in vapor-rich warm air off the ocean, which essentially forms a heat engine. And then hurricanes expand outward, limited by the availability of warm water. They're large enough to be spun by the Coriolis effect. And then hurricanes move across ocean basins driven by atmospheric currents, which we looked at in the previous slide. Hurricanes mostly occur between the subtropics and the equator, where ocean waters are warm enough to drive the engine. So with that, with the need for warm water vapor, each hemisphere is going to have a specific hurricane season. And with increasing ocean temperatures, we can probably expect larger hurricanes over time. So this diagram is showing us the motion of air and water in a supercell thunderstorm and related tornado. So in the Great Lakes region, especially in, say, August, you can look up often and see an anvil-shaped cloud, which that's a nice thundercloud. Um, Thunderstorms are columns of turbulent, moist air with variable amounts of lightning, thunder, rain, hail, and wind, and they usually develop that flat-topped anvil shape. When we say supercell thunderstorms, I don't know why I want to say thunderdome, but I do. Um, they are capped by a rounded upper dome, and that indicates strong updrafts. Okay, so we've got represented on here as I'm talking heavy rain and hail, and then rising, rotating air. Okay. Downpours are commonly associated with supercell thunderstorms. And then updrafts, uh, those would be upward moving winds, can result in tornadoes. Lightning actually results from electrical currents within the storm, like transfer of electrons and things like that. You can also have these strong local downdrafts. With that, you could see a microburst, typically producing winds that move in a straight line rather than rotating like a tornado. So tornadoes would be part of the updraft, and these downdrafts could get something called or result in something called a microburst. All right, if you have a small single cell storm, you're likely to have few tornadoes, which for us is a good thing. So where do tornadoes strike? You've probably heard of Tornado Alley in the U.S. That's where we get the most tornadoes. They form mostly in the central and eastern parts of the United States. Just looking at, the lower 48 here. The numbers in the legend indicate the average number of tornadoes per year. And I'm not saying why with this slide, I'm just saying where. All right, so this is the pattern of ocean currents. The red arrows are warm currents, like through here, and the blue arrows are cold currents. So what do you notice about the warm currents in red versus the blue currents and the overall flow? Well, currents flowing away from the tropics bring warm water. Okay, these are a little more cellular in shape than the cool currents. Ocean surface currents extend down to about 1,000 meters below sea level. Most are shallower, fast-moving streams driven by the prevailing winds. So currents flowing away from the poles bring colder water. Let's see. The blue lines, of course, indicate a relatively cool surface. And then, of course, the red lines are warm. These currents can combine to form that circular flow pattern in every ocean. They would then rotate clockwise in the northern hemisphere and counterclockwise in the southern hemisphere with the Earth's rotation. And surface currents can greatly affect climate along continental boundaries based on whether they bring cool currents versus warm. We actually call that a gyre, by the way, when you get a circular flow pattern. Okay. Still looking at this figure. All right. So we have a general correspondence of continents and oceans here. So starting off in the North Pacific, you have cool ocean water going to the south. Same thing with California. That's why this water is super cold. If you want to surf it, you should probably wear a wetsuit. And then the Gulf Stream carries warm water toward Europe. Along Canary here, we have a cooler current going to the south. And the equatorial currents are quite warm. Quite warm in the area of Mozambique. Cold along Antarctica. Cold along Humboldt. And cold going to the north with Benguela. All right. This is the spatial distribution of the average sea surface temperatures. We just call that SST. We can look at the main patterns here and consider the role of the ocean currents. And the main thing here is temperatures. SST is high in the tropics and subtropics, and lowest, of course, near the poles. Warm currents shift warm water toward the poles, and then cold currents move cold water toward the equator. We can call areas of very warm waters warm pools. Cold waters, of course, surround Antarctica. All right. So there is some control on temperature, of course, with latitude and, the sun's energy. There's a control on this based on the season. Like, is it the warm season or the cold season? We see western warm pools and eastern cooler areas, notably in the Pacific, and to a lesser degree in the Atlantic. And then we can detect traces of cool and warm ocean currents along various continental margins. And you can almost think of the Earth as continents that are just sitting in one ocean. We divvy it up, but what we can kind of take away from ocean temperature and ocean currents is that eventually they're all connected, moving around the globe. Okay, so the thermohaline conveyor. That speaks to the fact that global circulation of surface and deep water is driven by both temperature and salinity. So global oceans, we can say they're responsible for transfers of energy and for maintenance of global climate. This is driven, therefore, by differences in the density of seawater, which is controlled by temperature and salinity. So temperature is your thermo, salinity is the haline part. So the saline surface water in the North Atlantic sinks and flows south at depth due to greater density. And then cold, deep water in the northern Indian Ocean and the North Pacific, that can go up, and then its surface flow can then return to the Atlantic. This is important to global climate. So based on these differences in density, we're going to have global circulation. Okay, so how do ocean currents affect temperatures on land? I've mentioned that they do, but how do they? Okay, so with Australia, we have a warm ocean current coming down from the tropics. We also have prevailing easterlies winds that actually brings the warm, moist air to the land surface. We can also have, with this bottom figure, North Atlantic currents, winds blowing across the warm Gulf Stream help moderate temperatures across Europe. Okay, so you have warm air coming from the Gulf Stream toward Europe that way, with prevailing westerlies. Okay, SST differences during El Nino and La Nina. El Nino and La Nina are the, I guess what you could call the end member effects of the strength of the Pacific equatorial countercurrent, which flows east along the Pacific towards South America. El Nino occurs when the current is strong and extends or brings warm water to the eastern Pacific, leading to increased evaporation and increased precipitation on land. La Nina occurs when the current is weaker and ocean water temperatures in the eastern Pacific are cool, which then causes drier conditions on land. So the colors are showing you the SST relative to long-term averages. And to review that, you've got warmer water extending to the eastern Pacific. In La Nina, you've got warmer water mostly in the western Pacific. And that in turn will affect life in the sea and weather on land. So El Nino, we see that increased precipitation on land, and then La Nina, we see drier conditions on land. Okay, how a monsoon occurs. We're looking again at India as the focus. All right, and the Gobi Desert becomes a center of low pressure every summer as warm air rises from heated lands. So rising heated air causes low pressures. And then vapor-rich air from the Arabian Sea and the Bay of Bengal flows inward toward the low pressure zone, and with that it brings seasonal rains. As the vapor-rich air rises over the Himalayas, we see massive rainstorms. Okay. So you have this situation in the dry season, no clouds really hardly, and then the rainy season is a different situation. What you have in the rainy season, it's kind of hard to see, but there's a complete disappearance of a lake in the middle there. Just becomes mud or less than that during the dry season, and then it appears again in the rainy season. And that's along western India, which is a good segue into drought. So drought is an extended period of below average precipitation. And with that, it can be the result of a persistent weather pattern or change in ocean currents, causing an unseasonal shift in wind direction. With persistent high pressure, you could have sinking air that causes a region to be drier than normal. Or you could see a drought because of a temporary change in the direction or strength of an ocean current, and that could last multiple years. So all these things could be what leads to drought in a region. This is kind of a bigger thing to look at, the causes of seasons on Earth. The Earth's spin axis is tilted with respect to the Earth's orbit around the Sun. The axis is actually fixed in a position, so it varies in how it points relative to the Sun during a given year. So the northern hemisphere is angled toward the Sun during the summer, and at the same time, you have winter in the southern hemisphere, because it'd be angled away from the Sun there. At the opposite side of the orbit, then, the northern hemisphere is angled away from the Sun, so you have winter up there, and to the south you have summer. So it's based on the tilt of the Earth's axis as you orbit, with the Earth, orbit around the Sun. And we'll stop here for today.